Hi everyone, you're looking at a demo device that I've put together to demonstrate this effect of the coil being further away on the core material. And right here I have a Dremel tool that I have a diametrically magnetized cylinder magnet here. So half of it is north, the other half is south. That's a 1/2 inch by 1 inch wide, and this is a 1/2 inch core, which is more like just a soft kind of steel, cold rolled steel, I guess they call it, or whatever. Just buy that at Home Depot or Lowe's or whatever. And I happen to have this solenoid coil that was already wound that fits perfectly in that 1/2 inch there. So the Dremel tool now is being controlled by the variac, so I can adjust the speed very precisely, and as you can probably hear it, it's turning right now, and it's about at the slowest speed it can operate at. And the variac pretty well takes about 10 watts just sitting there. And now the device here, this Dremel tool, is using 8.4 watts. But I'm not just going by that. That's just the double check what's happening here. From the output of the variac here, it's going to the receptacle of this tool here, Dremel tool, and I have my voltage probe across the voltage, and I also have a current probe here. So that's measuring the current, and that is going to my oscilloscope. And right here on the bottom, if we look at the math, that is the amount of watts. So you're looking at pretty well the same thing. You were at I am saying 8.4 watts because there's about 10 watts just sitting there doing nothing. And if we look at our math, that is actually reflecting there perfectly, 8.37, 8.4 pretty well. And that is our voltage going in there, and that is our current in milliamps that the current probe is utilizing. That is the frequency of the coil right now. So the coil is right here across. And we're going to be looking at phase. So what I've done is I put this really thin pancake coil here right at the head of the core. So we've got a fixed sine wave here to be able to look at phase shift, what happens when the core moves up and down. So on that I have a 100 ohm resistor across this little thin coil. This doesn't produce any real current or anything. It's just a guideline to have a baseline to see where our current is at the head of this iron core here, or this steel core. So this is not the most ideal core material. It's just a solid bar, and it creates heat here as you increase the RPM. So here, what I can do with this coil here is I can slide that back and forth. So right now, if I slide it, I'm forward, fully forward. You just see the voltage going up right now. So both of them are in phase because there really isn't a load put on this coil here yet. So here I have loads. Right now this is a 0.1 ohm resistor here, and that would be pretty close to a short circuit, and I can still read voltage across it. And I have a probe here permanently connected across it. That's what you see, the blue trace. The yellow trace is the coil here, checking out for the phase position at the front end of the core. So I'll be attaching these loads, and we'd be able to see different effects. So I've got a 2 ohm there, I've got a 10 ohm, 47 ohm, 100 ohm, 220 ohm, and a 1K. So let's go ahead and attach one load. So I'm now attaching this 0.1 ohm, which would be pretty well equivalent to a short circuit. So right now our waveform has flattened out, and now I'll increase the voltage divisions. So now you can see that we do have indeed a phase shift between the current from the front end of the coil, sense coil, and to the back end coil here. And now what I'm going to do is I'm going to slide that core forward, that coil here on the core forward, and we'll see what happens. So I'm going forward, and as soon as I do that, the motor just stalls pretty well and everything stopped, because we have basically a short circuit across this coil here, and as we're bringing it in, it's having a hard time pushing against that amount of current that this coil is capable of producing. So obviously there's no special effect happening at a very low RPM for this particular coil, and what we can do now is we can just increase our voltage. Now I'm increasing the variac. Okay, so now we're at about 30 Hertz. And there's our front coil, and we do have a phase shift. And now what I'll do is I'll disconnect our short circuit here. And now you can hear the motor drop in RPM. And if you look at the frequency, we're at 21 Hertz. That's how much it's dropped. So now I'll connect the load. And now you see the increase in frequency. So obviously it's an increase in RPM, and we do see a phase shift happening. So obviously a certain frequency has to happen, and that has to do with the characteristics of the coil. Now what we can do now is, what do we have here? We've got 23 millivolts, which is like, you know, piddlings, okay? So if we move this forward on the core, we should have, okay, more voltage across. Okay, so now we're at 30 millivolts. And we notice our phase, but notice also that our RPM is going down, because this is a challenge for the prime mover. And the more you move it in, the more the prime mover is coming, and it's come to a stop. It's still, because it can't push that kind of current in there. Now if we go for a smaller load, or a higher resistance load, we'll put a 2 ohm load on that. And there we go. And now I'll drop my voltage divisions here. So now we have about 343 millivolts across our 2 ohm load there. And if we bring that in, it's the same scenario. Again, we've got not enough power to continue pushing against that. So again, what I can do is increase our RPM. So now we're in the 40 Hertz range. So let us go back and go to our, basically our short circuit. Here the RPM now, that with the resistor is off, and there we are at 30 Hertz. Okay, and now we're going to make our short circuit across the 0.1 ohm resistor. You hear the RPM increase. That's because the coil is at the furthest point here on our core. And let's look at what are we getting across here. So 0.27 millivolts. And what I'll do is expand here a bit on the times division, and we clearly see a good phase shift happening there. And that is what is causing this effect to operate, is that phase shift. Basically, by the time the current reaches its maximum here, by that time the rotor has already passed the sticky point, okay, and it basically traveling and attracting the next pole in. So that's why you get an increase in RPM. So just disconnect it to just show you. You hear it drop. And now you see this is our sine wave here from there to there. It's pretty close to being in phase with the front end sense coil. So connecting it back. Now let's move forward here. So here I am moving forward, and I'll show you there on the scope. So I'm back now, going forward. So we're getting more voltage across our load. Okay, so let's notice our RPM here. We're at about 44.4 hertz, and I'll bring it forward. And I can hear an increase in RPM. So yes, we are. So now we're at 46, 47, and I keep bringing it forward. Our voltage is going up across the resistor, but now suddenly we're back down to 44. And I'll bring the camera to show you where I'm at here on the core. So right here I would say would be the neutral point for this particular resistor load, and that would be about our peak without affecting the prime mover. So this is kind of giving you an idea of what's happening. There is our input power here. We're at 10.4 watts now, and there you go. So now what I can do is disconnect this, and we're going to connect the 2 ohm resistor. We get a slight increase, so let's start back here at the back end, and we'll change our voltage divisions here. Okay, so we're getting 349 millivolts across our 2 ohm resistor, and now I'm going to start sliding it forward. Let's look at our frequency, 42 hertz, and now I'm going forward. But all I'm getting is basically a deacceleration as I go forward. So what really happens is, as you increase in resistance, as you go up in resistance, this effect goes down. Okay? So your most ideal place is with a short circuit, but unfortunately with a short circuit you cannot get power out of it, power meaning in watts. So right now what I can do is I can just move over to a 10 ohm resistor. So here we have a 10 ohm resistor. And now I've collected the 10 ohm resistor, but the coil's at the furthest point. So we do have more voltage across our 10 ohm. We're basically at 1.4 volts, 1.5 volts. And there is our power in, and there's our frequency. Now I'll move that coil forward, see if we can get anything. And as soon as I move it forward, you see the frequency drop. And there is the sine wave. I'm back now. Now I'm moving it forward. So the only way that one could actually be able to power a higher resistance resistor, which would actually equate to more power out on this particular kind of device, is to increase your input so that your RPM goes up. So now our RPM is higher, and let's drop our voltage division there on our front end. So we still have a phase shift, we're still at the back here. If we notice, 60 hertz is our frequency right now, and I'll take the 10 ohm resistor off load, and you can hear it drop. Okay, and if we look at our frequency, we're at 49 hertz. So now, as you see, as the frequency goes up, you can power a higher resistance load and start to get more power out of the thing. Now, if you want to also get more power, you can bring this closer up to the front end, and that's what we'll do right now. So we're at 60 hertz, and we have 1.65 volts across, and now I'm moving it forward, and now you're seeing the sine wave go up in frequency. So now we're actually at 2.15 volts across. But as we're going forward, the more forward we go, and the more power we're putting across the resistor, we're starting now to actually lose RPM. So our break-even point is about right there. See, we're back at 60 hertz, and that is the position now. So there's our break-even point for that particular load resistor and that frequency. Now we could bring that further forward if we wanted and maintain without an RPM drop, but we'd have to increase our frequency. So this is how it all works. Now if I increase my frequency, let's start back. So we have 82 hertz, okay? And we have 1.69 volt across our 10 ohm resistor. So I'm going to start moving forward. And now you see our voltage across our 10 ohm resistor, okay, is going up. And our frequency, okay, is also going up. See here we're at 83 hertz. And here is where I am now. But if we keep going forward, eventually it's going to start reversing. So there we're at the point where it starts reversing. And that's how far forward I've gone. But yet, look at our voltage across our 10 ohm resistor. We're at 2.72 volts on our load. And we're at a break-even point now. Meaning if I disconnect that 10 ohm load, the RPM won't change. It'll stay pretty well the same. Well, now we've gone a little too much forward here, but if I bring it back a little, I can bring it back to our 80 hertz. Okay? But actually I haven't done our baseline check. Let's do that. So, okay, there, I take it off load. Okay, this doesn't matter where you have it. That's it basically turning. Actually, that's where I should have started. So it needs 65 hertz. Okay, is where it's turning at that point. So basically, we put our load resistor on. It goes up in RPM, and now we bring our head forward so that we're back down to about 65 hertz. And now let me adjust it. Okay, so about there. Now that's how close now I'm getting to the rotor. And now though, look at what we have across our 10 ohm resistor. 3.26 watts. So basically that's how this kind of system here works. And it's very interesting. I've been studying it for some years now. And I've made different kinds of coils and different kind of geometries. And I have one coil here that I just wound to make other demonstrations. But for now we're going to stop this video because it's probably going to get too long. I don't want to bore you. This coil here has an amazingly low resistance. We're talking about 0.00 something. It's so low it's unmeasurable for me anyways. So I'm going to be demonstrating what a very, very low resistance coil can do as well. And it behaves differently than a high impedance coil. And but yet you can also get acceleration happening out of that. And we can actually evaluate this you know, by using these different resistors. I'll tell you for sure that these low impedance coils would not be doing too well with these higher resistance value. It's going to be doing really well on a 0.2 ohm. It's going to put a lot of power across this. So this higher impedance coil here, by the way, that's about a I think that's a 6 ohm resistor, the DC resistance of that 6 ohm resistance. So anyways, interesting stuff, and hopefully some of you can put one of these devices together and test it for yourself and see this interesting effect and study it and find your ideal coil geometry. And then core, what we can do with that is obviously there are some higher quality cores out there that will be able to negate a lot of your eddy currents and your hysteresis. But I'm thinking that possibly hysteresis is part of the effect. It does seem to possibly help this effect. And the hysteresis is the ability for the core to change magnetic flux from in your sine wave. So if there's a delay in flux change, then possibly that might be a favor. So you might want to study this and do experiments to find out what works best. So that's it for now. Thanks for watching.